In this video, we'll be talking about the logarithm function for complex variables, and this is going to be a very important function later on when we evaluate complex integrals and things like that. So let's just start with the definition. So log z, where z is a complex number, so log z is any complex number w such that this relationship holds. It has to be true that e to the power of w equals z. So this is kind of an analog to the real logarithm function, but we see that if we take the real number e and raise it to the power of this w, we're going to get z back. And then such a w is called log z. So now how to solve this? We kind of went over this in the previous video, but we'll just do a refresher. So let's draw z on a complex plane. So let's say z is here. And as we saw in the previous video, z must have a modulus called modulus z. And then this angle we'll call theta. So as we saw in the previous video, the horizontal distance or the horizontal component of z is given by modulus of z cosine theta. And the vertical component is given by modulus of z sine theta. And don't forget the I, because we're going up in the imaginary direction. So, in all, z equals modulus of z times cosine theta plus I modulus of z sine theta. And then we can factor the z out and get cosine theta plus I sine theta. So that's good. We've successfully put the right side of this equation into the form we want. Now remember, the whole previous video is about e to the power of something. So we learned that we can write this as, and let's say w equals s plus it, where s and t are real, we can write e to the power of w as e to the s times cosine t plus I sine t. And now that has to be equal to modulus of z times cosine of theta plus I sine of theta. So we see why this is helpful, because we put it in this parallel form, and now we can kind of start equating things. So what can we start equating? Since this e to the s and this modulus of z is the modulus of the numbers we have on either side of this equation, they have to be equal. And we see that because if two numbers here do not have the same modulus, then there's no possible way for them to be equal, because one will be farther out than the other. So if they are equal, they must have the same modulus. So we see that e to the s must equal modulus of z. And now this is all real. This is nothing imaginary going on here. So we just take ln of both sides, and we get that s equals natural log of modulus of z. So that's good. We have that solved. Now what about this t and the theta going on? We kind of hinted at this in the previous video, but this is where we get an infinite number of solutions. So how to find the value for t? So t could equal theta. That's possible. But t can also equal theta plus 2 pi, or plus or minus 2 pi. In fact, plus or minus 2 pi n, where n is any integer. So in this way, we have an infinite number of solutions. So let's just write down what the solution is. So on this paper, we have found w equals s plus it, and we found the value for s is natural log of the modulus of z plus I, and t we found was theta plus or minus 2 pi n. So we see that in this way we have an infinite number of solutions. But even though this is great, we have an infinite number of solutions, this is kind of bad because this is not a function anymore. So that means that if we call w equals log z our potential function, a function must be so that if you put in a z, you get only one w back. You can't get two things back by putting one thing in. Otherwise, it's not a function. And that's exactly what happens here. If you put in some z, then you can get an infinite number of w just by changing this n to whatever value you want. So we kind of want to restrict this. We want only certain values of theta. And often, what is chosen is capital log of z. And this is called the principal branch. And we'll talk about branches right now. So this is kind of how this works. So if we have a graph, and this will be our domain. So it's all the possible values of z we can put in here to get values of w back. Now, if we, of course, we can let theta vary by 2 pi n. We can just keep letting it rotate around and around. But we want to restrict it. So we want to say, I'm going to restrict it here to be, it can go pi in this direction, and it can go to negative pi in this direction. And that's the only possible values of theta. So for example, if you choose here, let's say this is 45 degrees or pi over 4, this has to only be pi over 4, because you have to let the theta only be in the range of negative pi to pi. No other numbers are allowed. So for example, this has to be pi over 4. It can't be pi over 4 plus 2 pi. It can't be pi over 4 minus 2 pi. So that means that this is what this capital log z, or principal branch of log z, means. So just to get a feel for it, let's see what happens if you put log of 1 plus I. Okay, so this is good. We already have it drawn. Let's say 1 plus I is that red dot that I've drawn right here. So we know that to find that, if this is w, w has to equal natural log of the modulus of z, and the modulus is radical 2. So it's going to be ln radical 2 plus I times theta, and there's no longer this 2 pi n added, because we only have one option for theta. We must choose the one that lies in this range that I've written right here. And the only one that lies in this range is pi over 4. So this theta must equal pi over 4. And the answer is ln radical 2 plus pi over 4 I. And that is the singular answer, which means that this log z with a capital L is a function, because there's only one possible output for every input you put in. So that's good. But there's also something about this that's not quite good yet, because we also want this to be continuous. And here's the problem with it being continuous. If we start putting in values here, let's say we're going to work on the unit circle. And on the unit circle, modulus of z equals 1, which means that natural log of modulus of z equals 0, because ln 1 equals 0. So then w equals capital log z just reduces to I times, well, the angle that we choose. So now we're going to go down here. So here the angle is negative pi over 4, let's say. And then we go down negative pi over 2. And we just keep going. And now the angle is approaching what? Negative pi, because that's how we define the interval. So the angle is approaching negative pi, negative pi, negative pi. Then we just cross this barrier and the angle is now what? It's pi. So whoa, what just happened? We crossed from an angle of negative pi all the way to pi. So that is where this is not continuous. And that's kind of bad, because we would like it to be continuous. So now we ask ourselves, how can we make this continuous? And the answer is, we're going to choose a new domain. So here's our previous domain. We had chosen, well, the entire complex plane we had chosen. And we allowed this to go from pi to negative pi. So now what we're going to do is we're going to delete this negative real axis, including 0, the origin, which you can't put into the function anyway. And you're going to delete all of this. And so this is not part of the domain. You can't choose anything on this line to put on the domain. And all this might seem a little restrictive. This is why it helps, because now as you go over here, following this direction on the unit circle, your argument is, or your theta is rather, negative pi, negative pi, negative pi, and you can never get to pi because there's this restricted line in the way. And if you're going in this direction, your theta will be approaching pi, approaching pi, approaching pi, but you can never go down here because there's a thing in the way. So this is continuous. It's a continuous function. And that is how you define capital log of z. Now, this is only one branch. So to define a branch just means that it's something with one ray deleted. So a ray is starting at the origin and going in any direction. You delete one ray, and you choose the rest of the complex plane as your domain. And this capital log z is just the one that's most commonly worked with. But really, you can choose any ray. So if you wanted, you can have your own personal log z be if you just delete this ray right here. And then you also have to choose a range for the argument. So maybe in this case, you choose from pi over 4, so starting here, all the way around to 2 pi plus pi over 4. So what's 2 pi plus pi over 4? It's going to be 9 pi over 4. So 9 pi over 4. And that's your domain, which means that whenever you choose something over here, it's going to be greater than 2 pi. That's the theta. And this range of angles here, you can modify it as you wish, but you must make sure that the range, the length of the range is only 2 pi. So that's a lot about the log function. And in the next video, we'll talk about a few more applications of it before we move on to trigonometric functions.